Hi, so today we're going to go over some notes for matter and energy. And so this is the explain portion of understanding the heating curve and energy. So you just completed the lab activity that went over the heating curve of water, and we're going to kind of debrief that. But first, we're going to start with a chem catalyst. So in my class, the chem catalyst is the warm up to kind of get your brain moving. So a catalyst is something that's going to speed up a chemical reaction. So this is going to kind of speed up your reaction and being able to get ready for the day. So what gas is in the bubbles as water is boiling? So if you think about it, when water is boiling, and this was a question in your lab, when water is boiling, we have liquid water turning to water vapor. So what's happening in that situation is the water vapor is trying to escape from underneath the water, the liquid water. And so what's filling those bubbles is going to be water vapor. What will happen when heat is added to water that is at room temperature? So hopefully from our lab, you realized that when I have water at room temperature, which is what happened in the very last part of your lab activity, I had water at room temperature and I put it on a hot plate. So I added heat to it. And then when I added heat, all of a sudden, or I added energy, so heat is a transfer of energy. I'm adding that energy, and that energy is transferring into getting the particles to speed up, getting the particles to be moving faster. Okay, so you see that as an increase in temperature. But then all of a sudden, the temperature stops changing. And now all of that energy that's being added is being added into going towards changing the phase. Because all that energy that is going into changing the phase, what it's doing is it's getting rid of those intermolecular forces. And what I mean by that is the attractive forces that are between the liquid particles. When you pick up a water bottle, you would not have liquid water if there were not any attractive forces there. The attractive forces hold those liquid particles together, and that's how you end up getting something that you're able to drink. If there were no attractive forces, those particles would be all over the place and they would be a gas. So in this case, going back to the question, what will happen when heat is added to water that is at room temperature? At first, it's going to raise the temperature until it gets to 100 degrees Celsius. Then all of that energy is going to go in towards breaking up those attractive forces that are in the particles interacting with each other. When heat is added to a substance undergoing a phase change, what happens to the temperature of the substance? It is very important for you to understand that at a phase change, all of that energy is going in towards moving around those intermolecular forces, moving around or breaking down those forces that are keeping those particles close to each other. So, for example, for a solid, you have these vibrations. As soon as the attractive forces of the solid particles have been overcome, because enough energy has been added, as soon as we've overcome those attractive forces, all of a sudden we have a liquid. So, also, when you're going from a liquid to a gas, you have these attractive forces that are holding it into this liquid state. That's why with a liquid, you have this fixed volume. It might take the shape of the container because it's fluid, but you have a fixed volume. As soon as you start adding that energy towards that, at a phase change, all of that energy goes towards breaking down those attractive forces, getting rid of those attractive forces, and getting them to change phase. So all of the energy is the energy of a phase change, the energy required to change the phase. Now, in our lab, we looked at the independent and dependent variables in the temperature versus time graph. So when I'm looking at the independent is what's on my x-axis, it's what I'm changing. So I am changing time in that situation. The temperature is changing as a result of the time because I'm adding energy over time. So my independent is going to be my time, my dependent is going to be temperature. So I wanted to really quickly make sure that we connected on energy. So I wanted to make sure that you guys understood energy, number one, by definition, is the ability to do work. Energy is needed or absorbed, or it can be released in many processes. But the thing is, the energy has to come from somewhere. So we get our energy from the sun, okay? And the sun gets its energy from nuclear reactions. So we have these different types of energy. We have our nuclear reactions, we have our mechanical energy, thermal energy, electromagnetic energy, electrical energy, and chemical energy. So chemical energy is the energy stored between the bonds or within the bonds of chemicals. Electrical energy, think electricity. Electromagnetic, think about the wind turbines that you see when you head out to the desert. That's electromagnetic. What you have is you have a magnet that when those wind turbines are moving, you are sending that, you're changing the magnetic the location. So you're rotating around a magnet. And so what that's doing is that's generating electricity. Then we have thermal energy like heating. Mechanical energy would be like a moving car. That's your 1/2 mv squared. And then we have nuclear, and then you're looking at the sun. But the most important thing with all energy is the law of conservation of energy. So just like matter, first unit, we covered matter, the law of conservation of matter, the law of conservation of mass. Mass cannot be created or destroyed. The mass in the beginning is equal to the mass in the end. Same thing with energy. Energy cannot be created, it cannot be destroyed, but it can change. It can change what form it's in. So, for example, kinetic energy can be turned into potential energy. Think about a bouncy ball or potential energy. You're holding a bouncy ball up really high, you drop that bouncy ball, you had potential energy. All of that energy is transferred into kinetic energy because that's what gets it to move. Okay, so energy cannot be created or destroyed, but it can be transformed from one form to another. So this quick video is going to show you it's a time-lapse video of your heating curve of water. So you notice we have solid right there. You have your solid water or your ice, and you're increasing the temperature. As you're increasing the temperature, you're going from that negative value all the way up to 0. And then all of a sudden it starts to melt. Once the melting is done, you've started to change your temperature, and that temperature rises all the way up until eventually you're going to get to 100 degrees Celsius. And at 100 degrees Celsius, all of a sudden you're going to plateau again. That plateau always happens at a phase change. Something that's super interesting and important is that you recognize that your plateau for going from a solid to a liquid is much shorter than your plateau of going from a liquid to a gas, meaning it takes a whole lot more energy to transfer a substance from a liquid to a gas than it does to transfer it from a solid to a liquid. So this right here is your heating curve of water, and I would maybe take a moment and draw this. You're going to see it on the next few slides, but it's important for you to see you have your solid down here, and then at a phase change, you have both phases. So at your melting point, you have solid and liquid. At your boiling point, you have liquid and gas. And then as your temperature is changing, your temperature only changes when you only have one phase. So we have our solid, solid and liquid, liquid, liquid and gas, and then gas. This is our melting point where we're going from a solid to a liquid, or our heat of fusion is going to be our melting point, our energy required for melting. And then this right here is going to be our boiling point. Okay. Notice again, it takes a lot less energy to go from a solid to a liquid than it does to go from a liquid to a gas. Also, another thing I'd like to point out is the fact that when you are looking at going from a solid to a liquid, if you're going from a solid to a liquid, you are absorbing energy. So absorbing energy is endothermic. I'm taking energy in. And if you're going from gas to a liquid to a solid, this is called exothermic, or energy is exiting the system. Exothermic energy is exiting. So you have a release of energy. Going from a gas to a liquid to a solid. And that's because, so what's happening, you're releasing that energy. So your particles are getting closer together. They're slowing down, they're getting closer together. Endothermic means they're absorbing energy. You're absorbing energy, those particles are getting farther apart, they're moving faster. Okay. So when we look at this, so we still have our endothermic and our exothermic, but when we look at this, now we're looking at the particles. So when we're looking at the particles here, we're looking at the fact that the gas particles are much farther apart than the liquid particles. And that's a significant difference. Those gas particles are significantly farther apart. Going from gas to a liquid, that's called condensation. Going from a liquid to a gas, that's vaporization. Now, when you're going from a liquid to a solid, that would be freezing, and going from solid to a liquid, that's going to be melting. And again, remember that at these phase changes, at your B and at your D, you have both phases present. So you have solid and liquid here, and you have liquid and gas here. Now, here's the thing. It's really important for you to see that, notice there's no temperature difference here, or there's no temperature shown here. So I'm not telling you this is 0 degrees Celsius and 100 degrees Celsius. Now, you know for water, it's 0 degrees and 100 degrees. But this can be for any substance. So it's not just water, it's any substance. Any substance can go through this phase diagram. Now, here's the thing that's important, is this diagram is showing at constant pressure conditions. And we're going to talk about that the very last slide. But here's my question. How would this curve look different for something like methanol? Would it still happen at 0 degrees Celsius and 100 degrees Celsius? Not necessarily. So for methanol, you're going to end up having something that looks like this, where you have, and this is in Kelvin, it's not Celsius. So remember, degrees Celsius plus 273 equals Kelvin, okay? So you have at freezing, this is methanol. It was super, super cold. That's way below 0 degrees Celsius. And then you've got this big curve, and right up here, this is a little bit above. It's about, let's see, 273 is 0 degrees Celsius, and that looks like it's about it says 338. So you're looking at 65 degrees, so, or 65 Kelvin. So 65 Kelvin higher than the freezing point of water is where methanol becomes a vapor, okay? You still have a plateau here going from solid to a liquid, and a plateau here going from liquid to gas. Your plateau for liquid to a gas is much longer than the plateau from solid to a liquid. So I'm hoping in the end you can realize that the heating curves for all substances are going to look similar. What's going to make them different is what temperatures everything happens at, what temperatures the phase changes happen at. But you have that flat line, that plateau, that horizontal line occurs at every phase change for every substance. But again, we're looking at this in terms of a constant pressure. So looking at this, how do we figure out how much energy it is? Well, there's this study called calorimetry. So calorimetry is the measure of the heat change. Heat, remember, is a transfer of energy. Calorimetry is a measure of the heat change for a chemical and physical process. So a calorimeter is a device that's used to measure that heat change. 1 calorie is 4.184 joules. So if you ever look at the back of a food label, let's say you have food from the United Kingdom or you have food from Ireland, you're going to actually look at the back of that container, and it's going to tell you the amount of, so what we look at for food is calories, but in other countries, so they follow scientific measurement, and that's going to be in kilojoules. So we kind of need to know that conversion. We're going to do way more with this second semester. We're not doing very much with this right now, but 1 food calorie is the equivalent of 1 kilocalorie, 1 kilocalorie, and the lowercase calories are scientific calories, okay? So scientific calories here. And so 1,000 scientific calories is the equivalent of one food calorie. So, like, say you had something that was 120 calories per serving. That's really 120,000 scientific calories. Can you imagine them actually putting, oh, you've consumed 120,000 calories? That would make you feel pretty bad. So, in the end, they end up putting food calories. Food calories is that capital C. So just noticing the difference between the capital C and the lowercase c. Lowercase c is scientific calories. Capital C is food calories when we're looking at food. Okay, but calories are the amount of energy that are required to raise the temperature of 1 gram of substance by 1 degree Celsius. So energy, the process of energy being transferred is called heating. Heating is Q. Q is our heat, and we're going to look at two different types of calculations to figure out heat. Heat, Q, equals mc delta T, mass times specific heat capacity times change in temperature, or at a phase change, it's Q equals mass times the heat of phase change. And I would always give you the heat of phase change. Your change in temperature helps us to quantify how much energy is being transferred, okay? But it is important for you to understand that temperature is not energy. Temperature is a measurement of the quantity of how fast those particles are going, if you remember from your Eureka videos. So going back to our heating curve calculations, this would be really worth it to add to your notes. This is how we know which calculation we're using in each step of this graph. Here you have a temperature change. You have temperature going from -20 to 0. Because you have a temperature change, you figure out how much energy or how much heat there is with mc delta T. Remember, C is the specific heat capacity. I would give you that value, okay? Now your plateau, at a phase change, you're going to use Q equals m delta H. And that delta H could be fusion, it could be solidification, it could be vaporization, condensation. But at this point, you do not use mc delta T. The reason you don't use mc delta T is because your temperature is not changing there. So you're not going to use mc delta T here. You're using m delta H. So some of you are listening to this and going, I have no idea what you're saying. Here's the thing. Energy is required or released in different processes. In order to raise the temperature, we need to figure out how much energy is required, because the only way to raise the temperature is to take in energy. How much energy do we need to take in? Well, it depends on the mass, it depends on the substance, which is your specific heat capacity, and then it depends on how much we need to change the temperature. Okay, so now you have a bunch of ice and you need to melt it. How much energy is required to melt that ice if it's at 0 degrees Celsius? Well, it depends on the mass of the ice, and it depends on the energy required to go from solid to a liquid of whatever substance you're dealing with. So phase change, Q equals m delta H. Temperature change, Q equals mc delta T. So this graph, I think this graph is great. I would take a screenshot of this. This graph is awesome because what you're looking at here is you're looking at the energy, calculating the energy. So how do we know which equation to use? Well, if we're changing the temperature, we use Q equals mc delta T. So going from a negative value solid, going from a negative temperature to 0 degrees Celsius, say we're talking about water, you're going to use Q equals mc delta T, where we know ice has a specific heat capacity of 2.06 joules per grams degrees Celsius. Going from solid to a liquid, phase change, you use Q equals mH, because it depends on the mass and the substance. Remember, temperature is not changing at a phase change, so you can't use mc delta T. Going from liquid water to steam, 0 degrees Celsius, say to 100 degrees Celsius, you use the specific heat capacity, Q equals mc delta T. Your temperature is changing, you use Q equals mc delta T. At this point in this presentation, if you're not sure what each value means, Q means heat, M means mass in grams, C means specific heat capacity, which you'll see is measured in joules per gram degrees Celsius, joules per gram degrees Celsius. So again, Q is heat, M is mass, C is specific heat capacity. It's the amount of energy required to change 1 gram of whatever substance it is by 1 degree Celsius. And this delta, this triangle T, means change in temperature. And we're going to use Celsius here. Now, Q here is heat again, so energy transfer or energy required or released is equal to the mass, M, times H, which is the heat of our phase change. So when we're looking at the specific heat capacity, again, going back, what is that value? The specific heat capacity is the amount of heat or energy required to raise 1 gram of whatever substance it is by 1 degree Celsius. So do things that heat up faster have a higher or a lower specific heat capacity? The example I use here is, when was the last time you went to the beach? What if you went to the beach, you parked in the parking lot, and you realized, oh my gosh, I forgot my flip-flops. So now you run across, you've got your surfboard, you run across the pavement, the parking lot, and it's hot. It's really hot on your feet, right? Because that black pavement is going to absorb a lot of energy. Then you run onto the concrete, which doesn't feel as crazy hot, and that's because it absorbs energy differently. And then you run onto the sand, and the sand is like burning. But then you run into the water, and it's freezing cold. It's because water has a really high specific heat capacity, which means it takes a lot of energy to heat it up, and it loses a lot of energy cooling it down. So if you have a high specific heat capacity, it takes a longer time to heat you up. So the question is, do things heat up faster have a higher or a lower specific heat capacity? Things that heat up faster have a lower specific heat capacity. It doesn't take as much energy to raise the temperature. Okay? So if we have a question like this, how much energy is required to raise the temperature of 5 grams of water from 10 degrees Celsius to 45 degrees Celsius? What do we need to know? We need to know Q equals mc delta T, because we're changing the temperature. So C is 4.18 joules per grams degree Celsius. So Q equals M. Okay, my M is my 5 grams, put it there. C is my 4.18 joules per grams degree Celsius, put it there. And my change in temperature, I'm going from 10 degrees Celsius to 45 degrees Celsius, so 35 degrees Celsius. Multiply those bad boys out. See, notice that grams cancel, degrees Celsius cancel. You end with joules. 731.5 joules. We'll look at it in terms of specific or significant figures. You have 2 significant figures here. This one, I should probably have 10.0 there. We're going to round to 2 significant figures, 730 joules. Here's another one. What if we're changing the phase? How much energy is needed to melt 5 grams of ice? So you take your Q equals mH. Your M is 5 grams. Your H is 334 joules per gram. You end up getting 1,670 joules, or 1.7 kilojoules. So you'll realize really fast that in some cases, and in a lot of cases, it takes a lot more energy to change the phase than it does to change the temperature. Think about it. When was the last time someone tried to convince you to completely change your course, right? You're pretty young, so I mean, I'm sure that there haven't been huge, like, life-changing in terms of changing your course and the direction that you were headed. But when you try to change, it's like that whole teaching an old dog new tricks. It takes a lot of energy to change. So it takes a lot more energy to change something from a solid to a liquid or a liquid to a gas than it does just to change the temperature. So our last slide for today is this idea of phase diagrams. So what if our temperature and our pressure change? Well, then we have these phase change diagrams, and the dark lines represent our phase changes. So on the dark lines, you have both phases present. So here you have solid and gas present. Here you have liquid and gas present. Here you have solid and liquid present. And this point right here is called your triple point. At your triple point, all three phases are present. At your triple point, all three phases are present. Okay. And so if I change my pressure, say my pressure is 1 atm, and this is for carbon dioxide, 1 atm, and I'm at 0 degrees Celsius. Carbon dioxide or dry ice wants to be a gas, right? But what if I bring it all the way up to 72.9 atm and 0 degrees Celsius? Then it wants to be a liquid. How about if we have it at 5.1 atm and negative 80 degrees Celsius? Then it wants to be a solid. So from this diagram, this is what happens when we change the pressure and temperature at the same time. On the dark lines, that's where you have both phases present as you transition from one phase to another. At this point right here, it's called the triple point, which is where all three phases are present. Like always, if you have questions, please reach out. I'm here to answer questions. That was a lot of information. I would go back and replay this a couple times, slow it down, get down some good notes, and then make sure that you ask questions if you have any questions. Okay?